three laws of motions as we well know. The first of which is often referred to as the law of inertia. Objects at rest remain at rest. Objects in moving with constant velocity continue to move with constant velocity unless acted upon by some outside force. Very simple to understand, very easy to use. The second law of motion, probably the law that we will be using most frequently, is written as F net equals ma. This is a vector equation, and as all vector equations, they tell us two things. It tells us something about direction, in this case that the direction of the acceleration and the net force are the same. It tells us something about the magnitude. It says that acceleration is proportional to the net force and is inversely proportional to the mass. F net equals ma. Newton's third law of motion, the law of action-reaction forces, probably the most frequently quoted of Newton's third laws, the least understood, the most often misused of Newton's laws. Says that for every action there is an equal opposite reaction. Action and reaction are archaic terms for force. So what this is saying, every time you exert a force, there's an equal and opposite reaction force. Now, keeping in mind what we said earlier about forces, forces are always described in terms of two different objects. The object which is exerting the force and the object on which the force is exerted. The force exerted by A on B. When I push the wall, I exert the force on the wall, two separate objects. The reaction of that force is the force exerted by B on A. So the reaction is the force that the wall exerts on me. Action-reaction forces act on different things. We see that if the action is on B, the reaction is on A. Act on different things, and consequently, because of this, action and reaction forces cannot cancel. Forces cancel if there are equal and opposite forces acting on the same object. But in this case, the action is on B, the reaction is on A. These forces cannot cancel. And therein lies most of the misunderstanding related to Newton's third law of motion. As I said earlier, we will be using probably Newton's second law the most, which says that F net is equal to ma. In other words, we're going to be using this to figure out the acceleration, how the object moves. In order to do that, we need to know what the net force is acting on the object. And the net force is described as the vector sum of all the forces acting on this particular object. The net force on an object is equal to the mass of the object times the acceleration of that object. Since we need to know the net force acting on the object, or all the forces acting on the object, an important part of our solution will be this free body diagram. A free body diagram is a diagram of all the forces acting on the object. And we're going to use this free body diagram to determine the net force, and Newton's second law then to determine the acceleration. Well, of course, the direction of the acceleration will be in the direction of the net force. But we're going to use this also to figure out the magnitude of the acceleration, and that will be equal to the magnitude of the net force divided by the mass of the object. So what follows is a whole bunch of situations that will be described to you, and we will then proceed to draw the free body diagram of each of the following situations. Now, what you should be doing as a situation is described to you is to pause the video and draw the free body diagram, what you think is free body diagram. Following that, you can restart the video and a discussion will commence about the correct free body diagram. It's very important, these free body diagrams, because the problems will never tell you what the forces are. You're going to have to figure them out. And therein lies the difficulty in this problem. But once you have the free body diagram, it's fairly easy to figure out what the net force is and therefore what the acceleration is. And then your problem is solved. So let's move on to some problems, some examples, starting with some easier ones and going through some more difficult ones. A block of mass m moving at constant horizontal velocity on a frictionless table. So here we have a block moving with constant horizontal velocity on a frictionless table. Draw the free body diagram of the block. Okay, here's the free body diagram. Same two forces. The weight, force of the earth on the block, normal force, force of the table on the block. Again, the net force is 0 since the object is moving with constant horizontal velocity. Moving on, next problem. A block at rest on the table while being pushed to the left. This block is at rest. Draw the free body diagram of the block. Okay, the obvious vertical forces, the weight downward, the table upward, normal force upward. There is a push to the left, and that's the force of the finger on the block. But the block remains at rest, so there must be another force of equal magnitude to the right, and that must be a static friction force. So in this case, P and Fs are horizontal forces which cancel. Again, they are not action-reaction forces, but they cancel, giving us a net force of 0. Next problem, block M1 at rest relative to block M2 that is being pulled to the right by a horizontal string while on a frictionless table. So here we have M1 and M2, M1 sitting on top of M2, M2 is being pulled to the right, and M1 moves along with it. Draw the free body diagram of M1 and the separate free body diagram of M2. Here's the free body diagram of M1. There's the weight of M1 downward. There's a M2 exerting a force upward. That's a normal force. But there must be a force to the right on M1 because it is accelerating to the right along with block 2. And that must be a static friction force. Here's the free body diagram of M2. Its weight and the normal force of the table upward, that's N2. N1 is the force that M1 exerts on M2. And the two N1s, this N1, the force on block 2 and the force on block 1 are action-reaction forces, so they must be equal. This is the force that M2 exerts upward on M1. This is the force that M1 exerts on M2, and that force is downward. So these are action-reaction forces. Notice they act on different things. They don't cancel, but they are equal in magnitude, opposite direction. This force here is the reaction force of this force here. This is the horizontal force, static friction force exerted by M2 on M1. This is the force, static friction force that M1 exerts on M2. These two are action-reaction forces. They are equal in magnitude, opposite direction, and act on different things. There is the pull of the string to the right, and that's the tension, T. And so if we look at the net force acting on M2, that will be T minus Fs. And that must be equal to M2 times A. And if we look at the net force on M1, that'll be Fs, and that must be equal to M1 times A, and the acceleration of these two blocks are the same. So that's how you go about finding the acceleration of the block. Moving forward. Block M1 is held stationary by a string. Block M2 is accelerated to the right by a horizontal string. Friction between all moving surfaces, that is between M1 and M2, as well as M2 and the table. Draw the free body diagram of M1. Draw the free body diagram of M2. So here's a free body diagram of M1. Weight and normal force. There is a tension in the string, the upper string, T1 to the left. The string can only pull, remember. But there must be also a friction force, and this is a kinetic friction force exerted by M2 on M1 to the right. Since M1 is at rest, these two forces must be equal and opposite. They have to cancel. Here's a free body diagram of M2. Again, weight of M2, the normal force table. Here's the force exerted by M1 downward on M2. These two are action-reaction forces. This came out, the color's not right, but this is a kinetic friction force. These two are the action-reaction forces. The force of M2 on M1, this is the force of M1 on M2. Action-reaction forces equal and opposite. There is another friction force here in yellow, poor choice of colors, and that's the friction force of the table on M2. There is also the tension in the string, T2. So the net force on M2 will be T2 minus Fk minus this friction force down here. A single pulley supporting masses M1 and M2. Draw the free body diagram of M1. Draw the free body diagram of M2. So these are the free body diagrams of M1 and M2. Weight downward of each. Tension, the string upward. In tension, the string pulls M1 upward, the string pulls M2 upward. These tensions have to be equal, since what we have here is a massless, frictionless pulley. These tensions, and the masses are connected by a massless string, so that the tensions on a massless string that's wound around a massless pulley have to be equal. Same string, same pulley, same force. Okay, in this case, if M2 is larger in comparison to M1, then this M2 will accelerate downward, M1 accelerates upward, which means M2G must be greater than T. In this case, T must be greater than M1. So we can write the net force on M2 as M2G minus T must be equal to M2A, and for M1, T minus M1 must be equal to M1A. And solve for acceleration, solve for tension. Moving on, an L-shaped sled on a frictionless surface with an attached massless pulley, block of mass M on a frictionless surface of the sled, string connected to M, threaded around the pulley and pulled with a force F, is shown here. Draw the free body diagram of little m, draw the free body diagram of big M. So this is the free body diagram of the sled. Big mg downward, there's N2 upward. I have a N1, which is the force of M2 downward on the sled. The tension, I have two F's. I know I'm pulling this with a force of F, but the string is also pulling here with a force of F as well. So the total force of the string on the sled will be 2F. Here's a free body diagram of little m. There is, of course, the tension, and again, same string, same tension, F. Mg downward and N1 upward. Again, these two are action-reaction forces.